This question is about reaction rates. Aqueous iron 3 ions, Fe3 plus aqueous, react with aqueous iodide ions, I- aqueous, as shown below. A student carries out 3 experiments to investigate how different concentrations of Fe3 plus aqueous and I- aqueous affect the initial rate of this reaction. The results are shown below. Part A. Determine the rate constant and a possible 2-step mechanism for this reaction that are consistent with these results. Firstly, we need to determine the order of reaction for Fe3 plus and I-. Let's begin with Fe3 plus. So we're looking for where it has increased by a certain value. Here, it's increased by 2, and where I- has stayed the same or multiplied by 1. Then you need to look at the initial rate, and this has also multiplied by 2. Therefore, in the rate equation, we would write rate equals K, or the rate constant, square brackets, Fe3 plus to the power of 1, because Fe3 plus is a first order reaction, because when it's doubled, the initial rate is doubled when I- has remained the same. Then we need to do the same for I-. So we're looking where Fe3 plus has stayed the same. So for experiments 1 and 3. And for experiments 1 and 3, I- has doubled. And therefore we need to look at the initial rate. And it has quadrupled between experiments 1 and 3. Therefore, in the rate equation, we write I- to the power of 2 because it's a second order reaction. We can then use this information to work out K. And K equals the initial rate, so if we take experiment 1 and its values, it would be 8.10 times 10 to the 4, or minus 4, divided by 4 times 10 to the minus 2, multiplied by 3 times 10 to the minus 2 to the power of 2. And that gives us a K value of 22.5. Next, we need to work out the units. So the units for the numerator are moles per decimeter cubed per second. And for the denominator, it's moles per decimeter cubed multiplied by 3. And then if we were to cancel this out, we would end up with the units moles to the minus 2, decimeters to the 6, seconds to the minus 1. Because what I've done here is if we expand this numerator, we get the same thing. Expanding the denominator, we get moles to the 3, decimeters to the minus 9. Cancelling out the moles, we are then left with moles to the 2, and then cancelling out the decimeters, we're left with decimeters to the minus 6. But it's over 1, therefore it's moles to the negative 2 and decimeters to the 6. Finally, we need to work out a 2-step mechanism for this reaction. So we need a slow step first, and we can write this as a possible example, Fe3 plus aqueous plus 2I- aqueous produces Fe2 plus as our slow step. And then for our fast step, we then write Fe2 plus, so what we've just produced in our slow step, plus Fe3 plus aqueous produces 2 Fe2 plus aqueous plus I2 aqueous. And we notice here that if we cancel out the slow and fast steps, so that will be the ion we've created, we are then left with the overall equation we're given in the question. So we've got 2 Fe3 plus aqueous plus 2I minus aqueous produces 2 Fe2 plus aqueous plus I2 aqueous. And therefore we have been consistent with the results we're given. To get the marks for this question, you need to have produced a comprehensive conclusion which uses quantitative results for determination of the reaction orders and determines K from correct rate equation, which is what we've done in this question. Because there's an asterisk, there aren't specific marking points, but as long as you've been comprehensive and clear about your working, you've got the correct answers, you will get your 6 marks. Part B. A student carries out an investigation to find the activation energy EA and the pre-exponential factor A of a reaction. The student determines the rate constant K at different temperatures T. The student then plots a graph of ln K against 1 over T as shown below. Part 1. Draw a best fit straight line and calculate the activation energy in joules per mole. Give your answer to 3 significant figures and show all your working. Firstly, we need to draw our line of best fit. So we need a ruler, and the line of best fit does not need to intercept the y-axis here. We are just drawing our line of best fit for the range of the data points we've been given, like so. Now we've drawn our best straight line, or best fit straight line, we need to calculate the activation energy. In order to do this, we need to find the gradient of the line. If we take 2 data points on the line, 29 and 28, and see where they fall on the x-axis, we have 2.90 and 4. So the 2.90 for 29 and 4 for 28. But we need to pay careful attention to the units for 1 over t, times 10 to the negative 3. So when working out the gradient, we need to do 29 minus 28 divided by 2.9 times 10 to the negative 3 minus 4 times 10 to the negative 3. That gives us a gradient value of minus 909. The reason we've worked out gradient is because we're using the equation ln K equals minus EA over RT plus ln A. So by plotting a graph of ln K against 1 over t, we've got a y equals mx plus c graph, or a straight line graph. Therefore, the gradient is equal to minus EA over R. So in order to find EA, or the activation energy, we need to take the negative gradient, that would be plus 909, and multiply this by R, which is a constant you get given in your data sheet. You also get given this rearranged formula of the Arrhenius equation in your data sheet that we've used to plot this line. And that constant is 8.314, which gives you an activation energy value of 7,557.4. But we're asked in the question to give our answer to 3 significant figures. Therefore, that makes our final answer 7,560 joules per mole. To get the 3 marks for this question, you get 1 mark for working out the gradient correctly, 1 mark for then rearranging the Arrhenius equation and working out activation energy. And then you get 1 mark for using scales, so writing your answer to 3 significant figures, and also looking at the scale of the graph and noticing that 1 over t is 10 to the negative 3, so including that in your gradient. Those 2 points in this question get you your 3rd mark. Part 2. Use the graph to calculate the value of the pre-exponential factor A. Show your working. So also using this rearranged Arrhenius equation, EA is equal to the y-intercept And so in order to find a, or the pre-exponential factor, we need to find the y-intercept first. So extrapolating the y-intercept by continuing this line, we end up here. And this is 31.4 on the graph. So ln A is equal to 31.4, meaning that A is equal to e to the 31.4, which gives us the pre-exponential value of 4.33 times 10 to the 13, which is what we write on our answer line. To get the 2 marks for this question, you get your first mark for working out ln A is 31.4, or working out the y-intercept, and then your second mark for working out that A is e to the power of your y-intercept and working out that value.